quantum systems really are elements of possibility in a sense that exist outside of the space-time manifold. And so that these interactions are not literally things going forward in time or backward in time, but rather they're sort of possibilities that are in play.
The Rational View is a weekly series hosted by me, Dr. Alan Scott, providing a rational, evidence-based perspective on important societal issues.
Produced by Soapbox Media.
Hello and welcome to another episode of The Rational View. I'm your host, Dr. Al Scott. In this episode, I'm looking forward to exploring more about alternative interpretations of quantum mechanics. In previous episodes exploring consciousness, I've encountered several people who believe that quantum mechanics is at the root of consciousness. The hard problem of consciousness is supposedly explained by quantum mechanics. My current thinking on this is that this just replaces one mystery with another one without really providing an explanation for how consciousness arises. And maybe it's right. Maybe this consciousness is an aspect of the universe, is an aspect of a field or a wave function, a pre-existing property of some sort. But we're still stuck with the options of this or some sort of emergent property of a neural network or a processing network. Either way, quantum mechanics is an often misunderstood yet brilliant theory at the basic underlying portion of physics. It tells us that microscopic particles don't exist at a specific position with a specific momentum. They are, however, very accurately represented by something called a wave function. But nobody knows what this wave function really represents. It's been called the dreams that stuff is made of. They're used to calculate very accurately the distribution of a set of repeated measurements on identical particles. The process of observing or making a measurement, however, is poorly understood. In fact, it causes this wave function to collapse from a universal probability distribution to a single spot in time and space. The process of this collapse is not defined in the theory. There's a problem with quantum mechanics, and this is called the measurement problem, and it's never been adequately explained. And this is why there are so many different interpretations of quantum mechanics out there. For example, you may have heard of the many worlds theorem. This theorem posits that the wave function doesn't actually collapse. The wave function describes the continuum of all potential universes that could exist, and it says that they all do exist. And the measurement problem doesn't collapse the wave function to a point. It merely tells you which of these universes you're actually in. There are others. The Copenhagen interpretation is the mainstream one, where a measurement randomly collapses the wave function based on a probability, which is the amplitude of the wave function squared. And there are various mathematical tools which we can use to get these things. My current guest is someone who is a leading proponent of another interpretation of quantum mechanics called the Transactional Interpretation. If you like what you're hearing, please press like on your podcast app. Share it with your friends. I'd love to see you on my Facebook discussion group, The Rational View, or come visit my webpage at TheRationalView.ca. Dr. Ruth Kastner earned her master's in physics and PhD in history and philosophy of science from the University of Maryland. She has taught widely and conducted research in foundations of physics, particularly in interpretations of quantum theory. She was one of 3 winners of the 2021 Alumni Research Award at the University of Maryland, College Park. She's the author of 3 books: The Transactional Interpretation of Quantum Theory, The Reality of Possibility, Understanding Our Unseen Reality, Solving Quantum Riddles, and Adventures in Quantum Land, Exploring Our Unseen Reality. She's presented talks and interviews throughout the world and in video recordings on the interpretational challenges of quantum theory, and has a blog at transactionalinterpretation.org. She's also a dedicated yoga practitioner and received her 200-hour Yoga Alliance instructor certification in February 2020. Dr. Kastner, welcome to The Rational View.
Thank you very much. I appreciate the invitation.
So I've been doing a series of interviews exploring the concept of consciousness. And this is such a broad-ranging thought. There's philosophy, there's physics, there's neurobiology, so many different diverse fields of thought focused on what consciousness might be. And I've encountered several theories that link back to alternate versions of quantum mechanics, associating that with consciousness. Now, you're a lead proponent of what's called the transactional interpretation of quantum mechanics, which is one of these competing interpretations that physicists are trying, and physicists and philosophers are trying to work out exactly what quantum mechanics means. Because a lot of, if you ask a physicist and poke at them, they will say, okay, it's not a complete theory. There are problems. There's the measurement problem with this wave function collapsing. Could you give us an introduction to the transactional theory and maybe walk us through the major concepts of this idea?
Sure. So I guess I should. You're interested in sort of in quantum theory and the interpretations, and also you're kind of interested in how does consciousness fit in with all this. So, I mean, I should say probably right at the outset that the transactional interpretation or really formulation of quantum theory doesn't really. It's pretty agnostic on consciousness, so it doesn't have anything specific to say. It doesn't invoke consciousness in any explicit sort of way, but we can still talk about what might we learn from quantum theory that might have to do with consciousness, and that's an interesting question. But as to the transactional interpretation itself, you had mentioned that some physicists think that quantum theory isn't a complete theory, and traditionally, that description or that characterization of quantum theory as not complete was in the context of trying to add hidden variables to it. So, trying to kind of say, well, quantum theory seems to have these problems, and it seems to have this kind of indeterminacy and the difficulty of explaining how we get measurement outcomes, the measurement problem. And so for a long time, a lot of the approaches to interpreting quantum theory had to do with hidden variables, the idea that our quantum systems really do have some kind of hidden property or hidden feature about them that our quantum states just can't describe or can't get at. But if we kind of supplement the theory with these hidden variables, then we'll have some kind of a better understanding of our reality. Well, it turns out that that's fairly hard to do in a way that is fully satisfactory, in a way that is fully relativistically, meshes with the relativistic forms of quantum theory and so on. So, and it tends to do things like kind of pick out a preferred inertial reference frame, which you're not really supposed to do, and that kind of thing. So, the idea that the standard formulation is somehow missing something is an aspect of the transactional formulation, and what it really does is the transactional. I call it a formulation because in a technical sense, it's more than just an interpretation, because it really does feature a kind of physics. It has physical content that isn't in the standard theory, and that is basically a different way that the fields, quantum fields, by which I mean basically influences, that where a system can interact with another system. Those interactions are typically viewed as being mediated by fields, and the quantum systems themselves are seen as kind of field excitations that have a certain kind of description in terms of quantum state. And in the transactional picture, the fields behave very differently, and they've got this non-locality. So, in terms of the original formulation by John Kramer, who kind of created this original approach back in the 1980s, you have not only the sort of ordinary quantum state that has a kind of forward-directed component to it, but you also have a response that is actually kind of past directed, which is called an advanced state of the field. And I mean, it gets quite technical, and I don't know how much technical detail you want to go into, but sort of at the nutshell version, sort of the primer version, and you can always go into more detail, but the primer version is the idea that what's missing from the standard theory is not simply something being emitted, which is called the offer or offer wave in TI, but something actually coming back and responding to that. And when you include that absorber response, then you get measurement and you get a very clear idea of, what is it that's physically going on when we do a measurement. So that's kind of the very, brief overview version.
Yeah, that's great. So the terminology is a little bit confusing. There's an offer wave from a particle that might emit something, and another wave that comes backwards in time from something that might receive that energy or that particle. Is that correct?
That's correct. But what the thing that really gets problematic and confusing is the idea of things going backward in time. Well, how is it? Does that mean the future is sending signals back in time and so on? And I don't view it that way. I think that in my work, what I argue is that quantum systems, quantum states are really not space-time objects. So this is a bit radical. It kind of requires a kind of a retooling of our conceptual approaches to understanding reality. But it's the idea that these are kind of, that quantum systems really are elements of possibility in a sense that exist outside of the space-time manifold. And so that these interactions are not literally things going forward in time or backward in time, but rather they're sort of possibilities that are in play that have a kind of time symmetric character simply because they aren't actualized yet. So you typically will get what's called an offer that has different components that reach a bunch of different absorbers that would be eligible, say, to maybe receive a photon, the photon that is possibly is being offered. And so these different absorbers are going to send back a component of what they received, and you basically get kind of a competing set of what I call incipient transactions. And only one of these can really be actualized such that the photon goes to one of those responding absorbers, but not to all of them. So that corresponds to the collapse that we get in measurement.
Okay, so this represents the collapse of the wave function that you want from standard quantum mechanics one expects during measurement. There's a collapse from a set of probabilities, which is represented by the square of the amplitude of the wave function, and it collapses into one of these things based on that probability distribution. And so from the transactional theory, the collapse occurs when an offer wave goes forward and what's the return wave called?
It's called a confirmation wave.
Confirmation wave comes back, and all of these then will interfere, I assume, following the same rules of quantum mechanics?
They don't actually interfere. Yeah, this is the interesting thing. What you get, interference takes place at the level of a single offer component or sometimes a single confirmation component. But once you get what you get when you get these responses, they are actually very almost like collimated. They're targeted so that the technical expression of it, it becomes clear when you look at the math, but the technical expression of this is that they each have their own separate character, so that each of these, what I call incipient transactions, are really just an offer component and its absorber response that matches it. And they set up a kind of a what's described by what's called a projection operator in quantum theory. So these are sort of these are entities that are autonomous in a sense. So you have a projection operator for each of these incipient transactions. They don't mutually interfere. They have a kind of an autonomous character, and they each have their own weight that is this probabilistic weight that you get by technically taking the outer product of the offer wave component and the confirmation wave component. So once you get that interaction, it's called a non-unitary interaction when you get this absorber response going on. You really do get this kind of autonomous set of projection operators, each of which corresponds to an outcome. So it isn't a case of just kind of an interfering ordinary little wave function that has interfering components. The interference actually gets broken by this absorber response.
Okay.
And if you look at the math, it's got a mathematical representation that kind of captures this, what's called non-unitarity.
Okay. So there seems to be a lot of machinery to this interpretation. What problems does it solve? If we are to posit that this is the proper interpretation of quantum mechanics, how does that improve our understanding of quantum mechanics?
Well, what it does is it actually explains, it gives you the physical process that underlies a lot of expressions that we already use in quantum theory, such as, von Neumann, who was this brilliant mathematician who constructed a mathematical formulation of quantum theory that had all these kinds of processes in it, in mathematical form only. So he kind of said, okay, well, sometimes it seems like we've got a certain kind of evolution that the technical term is unitary, which means it's just kind of force-based, the action of forces. And then sometimes we have this measurement transition, and he didn't know, he couldn't say what causes it, but he said this is its mathematical character, and he represented that mathematically. So that was a very useful representation that seems to, when you use it as a recipe, it corresponds to what we see. But it was very mysterious as to, well, what is it that causes this, what's called a pure state, that I prepare my system in a pure state, and then it somehow transitions into this mixed state, which von Neumann was correct that is the correct mathematical representation. What I just described with the transactional picture actually gives you this transition from your pure state, your pure unmeasured state, to what's called a mixed state. That is just that set of projection operators with their weights. So it sounds, when you describe it in words, I've got this offer wave and I got that confirmation wave coming back, and it sounds kind of, why? Well, that sounds really, really unwieldy. But in fact, it corresponds perfectly to the mathematics that we already use in the theory. But without the physics of the transactional picture, it just becomes some mathematical recipe that you don't know why it works, and you don't know, you can never say, well, at what point has a measurement taken place? So that's why we get the Schrödinger cat paradox, and we get all these paradoxes of Wigner's friend paradoxes. And those, you only get those because you're not able to say what's triggering a measurement transition. So with TI, you can very, quantitatively point out, it's not deterministic. I mean, you cannot predict at time t, I'm going to have a transactional process. You can't do that because quantum theory is really fundamentally indeterministic. But you can give a quantitative description that will give you the probability, say, that any particular time t, under certain conditions, given, what kind of atom I have or whatever, that I'm going to get a measurement transition. So it really solves the measurement problem in that respect.
So this gives an objective criterion or an objective explanation of how the wave function collapses to it projects onto reality, effectively onto a measurable real world state from its multiple overlapping probabilities. So how would this change the Schrödinger's cat experiment? This is, the Schrödinger's cat is a very popular and well-known thought experiment about there's a cat in a box with a radioactive source and a poison gas vial, and if the radioactive source gives off emits a particle within its half-life, then the gas is released and the cat is dead. But if you don't open the box, quantum mechanics says that they're in a superposition of dead cat and live cat. What does
the standard theory does, right? What TI does is it says, okay, well, the standard formulation is missing some of the physics, and what it's missing is the idea that atoms. We could get into some technical subtleties if we dealt with radioactive decay. So I'm going to discuss it, and it still works out, but we'll discuss it in terms of, suppose we just had an excited atom, okay, that could give off a photon, okay, so it has some probability, but this is basically a decay rate. So it has a rate of decay such that it's has a 50% probability within, say, an hour that it has decayed. But with TI, what happens is decays don't occur unilaterally. So the only reason you get this kind of decay process is because you've got an interaction between the emitter, which is the unstable atom, and all the absorbing atoms that are present, in this case in the Geiger counter or whatever it is that's going to provide the absorption for your photon. So instead of kind of just this superposition that is in this pure state, what you get with the transactional picture is you really get this mixed state that gives you a probability for any time t that you're going to get this photon emitted and absorbed. So rather than have a superposition, you've actually got a set of projection operators with a very well-defined probability. And the reason, and so what's going to happen is that it's the absorbers in the Geiger counter that are going to trigger a collapse long before any sort of a macroscopic object like a cat can become, part of the superposition. So it by circumscribing the decay process the way it does, it doesn't let decays just kind of happen unilaterally. They only happen because there are responses, absorber responses. So when you're getting these responses, that's what's triggering this transition. It's a real physical transition that's missing in the standard picture. So even though it's indeterministic, I mean, nobody can predict when you're going to get collapse, but the probability of collapse is overwhelmingly huge that it's going to occur with respect to these microscopic systems rather than, an entire cat.
I see. So in this case, you can't have you typically don't have macroscopic superpositions in this theory. The wave function will automatically or it will collapse when the interaction happens, and you can't be in a state where it may have happened or it may not have happened. It's going to collapse.
Right. Yeah, and the key here is that really the probability of a transactional process, which is what triggers measurement and collapse, is overwhelmingly large for any kind of system that approaches macroscopic proportions. So in the theory, I present this I have the latest version of my Cambridge book that just came out this past month, where it's the second edition of that book, where it does go into some quantitative detail that shows exactly why for more and more complex objects, more macroscopic kind of size objects, the more overwhelmingly likely it is that you're going to get this transactional process within a very short period of time, so that you're not going to be able to get these kinds of superpositions. And it corresponds perfectly to the decoherence that we often hear about. We often hear the word decoherence in the traditional theory, but in that context, it's kind of missing some crucial content, so it becomes a bit hand-wavy and a bit circular. But I've been showing how we get this real physical decoherence in the transactional picture that really leads to collapse as an objective kind of physical process.
So can you contrast this with the standard Copenhagen interpretation? Are there any predictions from this that would be measurable or observable that would differentiate this from what people typically think of when they're, spouting about the Schrodinger's cat?
Well, this is an interesting question because at the level of the Born probabilities, these two formulations are completely equivalent. They're empirically equivalent in that, and this is actually a theorem that you can look at the relativistic level, that the field behavior in this what's called the direct action or absorber theory is actually empirically equivalent to the standard theory at the level of probabilities. So, people are often, they'd really like it if we could say, okay, here's a test, where TI predicts something that would be like an experimental way to discern experimentally between these two. But what I'd like to point out, I guess, is that we do have an anomaly in an anomalous situation in the standard theory, which is that we experience empirically measurement results. We get measurement results. And the standard theory is unable to explain that. So at the level of, at that empirical level, that, okay, empirically we find specific, unique experimental results. We don't have cats and superpositions and so on. Well, this is what TI predicts. This is what the transactional interpretation actually predicts. It predicts that you will get a measurement and a collapse, under these specific conditions. Whereas the standard theory, that is the measurement problem, that the standard theory fails to predict measurement results and even fails to be able to say what measurement is. So I'd like to kind of, make that distinction at the level of the probabilities, we are the same. The probabilities are the same. However, the standard theory just can't account for our empirical observations.
Right. That's the measurement problem. It just doesn't say what an observation is and who is an observer. It suffers from this horrible lack of definition as to what an observer is. And there's been all sorts of speculation whether it requires intelligence, and you've got Wheeler and the group, thinking of all sorts of different ideas about, people thinking that you need intelligence. Is that an observer? Is an observer just an interaction? So this basically clearly spells out that it's an absorption of, is it absorption of energy that is required, a transfer of energy from one particle to another? Do we have a clear definition mathematically of an absorber?
Yeah, an absorber is basically a field source that can respond. So I mean, basically, what triggers this measurement transition, what precipitates the measurement, is absorber response. And actually, that's a non-relativistic statement. That at the relativistic level, what you really have is a kind of a mutual interaction that is non-unitary. So there's a particular kind of emitter-absorber interaction, and the basic probability of it is governed by the fine structure constant, which is basically two factors of the charge of the charge of your electron or object that is the source of the field. So again, it's indeterministic. And but it is a specific non-unitary interaction. So we kind of have two levels in this transactional theory. We have at the level of force, we have what's called a unitary interaction, and that is just a direct connection. So suppose you have, when you have two electrons repelling one another, now that's not a measurement. Okay, so we could call that just scattering. Okay, so what's called the scattering process is not measurement, but what it is, it's the technical term is they have a direct connection via the time symmetric propagator. So that's for people who like the technical details. Time symmetric propagator connects these two charges, and there's no fact of the matter about which one's an emitter, which one's an absorber. They're simply field sources and they interact this way. But it's non-local, and that's why it's kind of challenges are, we all have been kind of marinated in our macroscopic, experience that we want things to be causal, we want things to be local, and so on. So this theory kind of challenges that. But that's what forces are in this theory. They are this kind of direct connection. Now, what's required to have a measurement, which is a different, higher level kind of interaction, is that we have objects such as maybe atoms that have internal energy states. So rather than just a couple of electrons, we need some structure. We need some additional structure, such as, say, hydrogen atoms. Okay, so take a couple of hydrogen atoms and take one that's excited, in an excited state, so that its electron is, at a higher energy level, and then another one that's at a lower, say, a ground state. Well, now we have the potential for a measurement, for a transactional process. And it's again, it's indeterministic, but this is where our decay rates come into play. So there's a clearly defined probability for any particular time that these two atoms will go, hey, we're going to do this non-unitary, we're going to elevate our interaction from simply force-based to be able to transfer energy. So here we distinguish energy from force, and we get the emitter emitting an offer wave, and we get the absorber responding to that. And if we have more than one potential absorber, then we get a bunch of them responding. But this isn't really real energy. It's kind of the possibility for energy. So what we've got is, say, suppose we had 3 eligible ground state atoms that could absorb it. They would all respond with what would be represented by a projection operator again. So we'd have our measurement transition, our mixed state, but only one of these could actually get that hunk of real energy that is the photon. So there's sort of 2 stages to the measurement transition. There's the response. There's the initial non-unitary interaction that involves this kind of response and the creation of this set of weighted possibilities that have well-defined probabilities. And then there's a collapse to one of them. So, it's kind of it's a lot of words, but it's very clearly, you can quantitatively define it. You can, the probability that's going to happen at any particular time and so on.
This is very interesting. So the collapse of the wave function is still to a random possibility amongst the options, weighted by the probability of these things. Now, this has been used by a lot of people that I've talked to, this randomness in quantum mechanics as a place to hide the will of the gods, or the place to hide volition and free will and consciousness. It hides in this randomness of the quantum mechanical measurement, the indeterminacy of quantum mechanics. So does the transactional interpretation close this gap? I guess the gap still is there. There's still no explanation as to why one is chosen over the other.
That's correct. It is, and that's what you get with genuine indeterminism. So, rather than the term randomness, I like to just use indeterminism. It's a one-to-many kind of transition. You get, this some prepared state transitioning to several, or many different possibilities. And this actually does happen elsewhere in physical theories. You have what's called spontaneous symmetry breaking in connection with the Higgs mechanism, where you have a bunch of different possible vacuum states for the field, and there's kind of no explanation. There's no causal account for why one of these gets realized. So we do have this elsewhere in physics. So I always point that out when people kind of say, well, you haven't solved the measurement problem because you haven't explained, why I got this one outcome. And so the point is, well, that doesn't mean we haven't accounted for what measurement is and so on, because you have the same situation elsewhere in physics with spontaneous symmetry breaking. So, that's one way to understand it. I do think I've written a little bit on this point, although I definitely don't focus on it and don't claim to have any special expertise in issues of free will and so on. But I do think it's true that if your world were completely deterministic, then I dissent from the idea that people who call themselves compatibilists will say things like, well, free will is compatible with determinism, and I dissent from that, because if if physical law, and there's a famous argument by someone whose name I'm forgetting now. I think it's Genet, but others have made this argument too. If physical law is deterministic, and the initial conditions of all our physical laws were set up, way before we were born, then how could anything that we do possibly be up to us, right? And it's just sort of whatever's going to happen is literally predetermined. So I really don't think compatibilism works at all, and I think it's kind of a form of denial. However, if the world really is indeterministic, if physics really is at a fundamental level indeterministic, then that's the only thing that could possibly be, I think, in my view, an entry point for volition. That where else could it come in? I'm not sure where else it would come in. So if those of us who do think we have free will, this is good news. And I mean, it's who knows how that gets implemented. I don't claim to be able to explain that, but certainly there's at least an entry point where whatever happens in the future is not clearly not fated if physical law itself is unable to tell you what's going to happen. So something either nature chooses, or many famous physicists have talked about choice or nature choosing. Freeman Dyson has talked about that. So it seems that at some level, some kind of acausal, if you will, process is happening that could correspond to volition at some, in some way.
I struggle philosophically with this whole thought about free will and determinism, because I'm kind of on the fence in all of this, because if indeterminism allows free will, then we should be able to influence the probabilities of quantum mechanics with our free will. And I've never seen an experiment that can show that.
Oh, actually, though, I don't think that necessarily follows. So the idea that the idea that because that the fact that we might be able to choose, given, suppose we've got 3 places for a particle to be, 3 boxes or something, and we can somehow precipitate box A. That doesn't necessarily mean we've influenced the possibilities. So, but I mean, it's a subtle point, and I actually have written a paper about this very point. So I could give you that. I can dig it out and give you that, and we can at some point put it in the chat, or put it in some comments for people who want to look at that. One place to start is a paper by Clark. I'm forgetting his first name. Randolph Clark. Anyway, I will dig. It's in my paper. And he has this wonderful paper entitled "Are We Free to Obey the Laws?" So it's sort of like, can you have freedom? Is there a situation where someone has different choices they can make that have to be distributed according to some probabilistic law, but for any given instance, they can choose, which outcome is going to be realized as long as the distribution ends up being in accordance with that law. And you can do that. I mean, you can actually do that. So the idea is, it doesn't necessarily require, in order for us to kind of take advantage of this loophole and have free will and say, okay, the quantum probabilities are such and such, and therefore, if I choose, I'm going to change them. And it actually doesn't follow. Another reason it doesn't follow is that at the level of the kinds of macroscopic situations that people would be involved in, it is not the case that well-defined quantum probabilities apply to those. So let me try to see if I can explain this. So suppose, we're talking about a typical choice like, well, should I have coffee or tea, after dinner? Okay, well, it is not the case that there are well-defined quantum Born rule probabilities for those choices. In fact, there are a bunch of different brain states and different environmental situations that are in play for corresponding to that choice. So the only, the idea that this is another mistake that people make. They'll say, well, there's a paper that I've also critiqued in the paper that I need to give you the reference for, where a philosopher is saying, take the case of Hitler. Okay, so Hitler is a terrible example. I don't know why he came up with that, but so for the quantum probabilities applying to Hitler are 90% invade Poland, 9% invade France, 1% become a ballet dancer. Okay, if Hitler could really choose freely, then the arguments, the idea is that Hitler must be a slave to these probabilities. He has to be bound by these probabilities, so therefore he doesn't really have free will in some sense. But in fact, these choices are not described by quantum observables. Right? You in order to get a born rule probability, you must have a well-defined quantum mechanical observable that corresponds to a particular, set of degrees of freedom, and you just don't have that at the macroscopic level for people like Hitler, or people deciding what beverage to have. There's no well-defined quantum observable in play. So the idea that we are slaves to the probabilities, I think, is really overstated. And I think that there's a genuine, entry point to have where we've really got indeterminism, and that's our entry point for volition.
Yeah, the fact that the indeterminism allows for different futures is effectively the argument that allows us to influence with our free will the future, versus determinism, where the future is set and we cannot change it, so it appears we don't have free will, even though the things we are doing are in line with our volition or our wants and needs. I think Bertrand Russell had a very good description of, determinism doesn't get rid of free will. You are still acting with your own volition. I mean, nobody can predict the future. There's chaos.
Did Russell say that?
Yes.
Sounds like that's a compatibilist argument, and I'm like, well, no, I'm sorry. If the laws of physics are truly deterministic, then the so-called volition that I really want some tea, so I'm just going to choose tea. Well, no, I'm sorry. According to the assertion, if one is going to assert determinism, then one must assert that their desire for tea has been determined by physical law, and it's not up to you. So I just see people wanting to have it both ways. I have to go back. I don't know. I don't want to be like saying Russell was refuting himself, and unless I know that. But this is a standard argument. I think there's a philosopher named Stamp who made this sort of argument that well, compatibilism. Okay, if no one is coercing you, then you have free will. If you're not actively constrained by some, then you have the free will to act in accordance with your desires or something. But again, this is trying to have it both ways, because if one is going to assert determinism, then one's desires are simply determined, and we're just dominoes, right? I mean, that's the domino picture. So, I don't believe the universe is deterministic. So that's not a problem for me. But if someone wants to assert determinism, then really they're just saying we're sentient dominoes. Because, you just initial conditions, deterministic laws. I'm sorry, folks, there are no live choices, because the laws decree unique outcomes for everything. So I just, I kind of go on a tear about that, because I just, a lot of people just really want to have it both ways. So yeah. I mean, I'm happy to learn. Like I get told that I'm caricaturing compatibilism, but again, I just, I'm receptive to being challenged on that. But it does seem as though if you've got determinism, you've basically got people being sentient dominoes.
I'm not the greatest proponent for this either. I'm not a philosopher, but uh, I'm very interested in all of these arguments, and I haven't, as I say, I'm pretty agnostic at this point. I'm learning all the time about a lot of these positions, and it's quite interesting to see. How has the reception been for transactional interpretation in the physics community? Is it picking up steam? Is there a large group of support, or is it relatively
I
new
think
to most
it's
people?
picking up steam. It's sort of the little engine that could. Uh, my husband happens to be really interested in steam locomotives, so it's a metaphor that he does these live steam trains where they
Oh,
miniature
cool.
trains that actually run on live steam. But anyway, so it has the kind of stigma of Wheeler and Feynman, who were among the original proponents of this absorber theory, both kind of walked away from it at some point because it didn't
Hmm.
really serve their purpose at the time, but it does work. And it's simply that, I go into this in some detail in my book, that it didn't serve the purpose they were pursuing it for. Um, and so it does have this kind of stigma, oh, these smart guys, didn't continue with this theory. And it also does have the non-local direct connection, which is viewed suspiciously, action at a distance and that kind of thing. So it is gaining some more, maybe not acceptance, but interest. So I think it's starting to be considered a little bit more broadly, which is nice. And I mean, it is true that back in about 5 years, I think, before Wheeler passed away, he actually came back to it and started saying, the absorber theory may have promise for quantum gravity and so on. So it does have to overcome some amount of stigma due to its historical status and the kind of counterintuitive features that it has. But
Well, yeah, and I kind of like the grandiosity of the many worlds theorem to a certain extent, and this kind of slays that, gets rid of all those other universes.
well, yeah, the many worlds thing, I think, was a noble effort by Hugh Everett to kind of bite the bullet of, look, quantum theory, if you really think that it only has this unitary evolution, which is what people kind of tend to think, that it really only has unitary evolution, then there's no real collapse. And he kind of, wanted to be honest about that and say, okay, well, then there's no collapse. Let's explore that. But I've argued it just doesn't really work because it does not lead to the kinds of empirical, fruitfulness that it doesn't really predict what we see. And in order to kind of get the Born rule out of it, you kind of use circular argumentation and have kind of a preferred basis for how the world splits and kind of smuggle in classicality, and it gets a bit circular. So I just think it really doesn't work. And I think that it's important in order to make progress with these kinds of increasingly bizarre, paradoxical situations that people are coming up with Wigner's friend, and we really get kind of inconsistencies happening now, and those are not. I've argued those are not really. You can't really get around them in the many worlds picture because you end up just kind of hand waving and saying, "Oh, where is splitting going to happen, and why should splitting happen for this interaction but not for that interaction?" And it becomes kind of ad hoc, and so I do think that there is real non-unitarity, the technical term meaning this transition from just the mere kind of force-based deterministic process to the indeterministic process. This is really happening in nature, and the transactional formulation is the only one that gives you kind of a natural physical basis for that without having to kind of jerry-rig quantum theory and put in ad hoc kinds of things.
This sort of providing objective criterion for decoherence or for collapse pops up in a lot of theories. I know Penrose has his objective reduction theory as well, and he tries to tie in quantum gravity to the criteria for an objective collapse criterion, effectively. And so for these ones, I mean, you could envision a refutation or an experiment where you could try to put macroscopic things into superpositions. Are there any efforts going towards these sort of experiments, or any realistic hopes that something could happen to, try a refutation or experiment and discern between some of these?
Yeah, I mean, again, for the transactional picture, it is empirically equivalent at the level of the Born probabilities, because as we've talked about, it derives those. So, and what you get with TI again is that it resolves the anomaly of failing to get measurement in the standard theory. However, for these other explicit collapse theories, they do seem to deviate. They do deviate, I think, and I'm not expert on that. I happen to think the Penrose, approach, again, it is very nice to look for some real non-unitarity in nature rather than just using your, observers as your placeholder for I don't know what, right? I don't think that's really the right way to go, because I do think that gravitation is an emergent, basically the structure of space-time that emerges from measurement, and that's what I've argued. So I don't think you can kind of use gravity to do that, and I think that's why they're getting. I mean, who knows? Again, if it is falsifiable, then or if it is something where it could be corroborated, well, that would be good information. I do think that from what I've heard, there are some perhaps experiments that are being contemplated that might be able to distinguish the Penrose model, that or falsify it. So, and I do think for the other explicit collapses, because they do have to change the theory, they have to change the dynamics, that does change the probabilities to one degree or another. So for those theories, which I view as kind of ad hoc, I view them as kind of ad hoc changes to kind of force collapse. But it is, I believe, the case that that's what they're aiming for, to get a test like that.
You mentioned in passing that you've worked on your theory of this is saying that gravity is emergent from this picture, that and time, these are timeless type of interactions. You've also mentioned that. So are you thinking that relativity and gravity and all this stuff kind of emerges as something that's not basic, that the quantum mechanical structure is the basic thing, that structure of reality, and relativity emerges then from this as a consequence?
Exactly. Yes. I mean, I've argued kind of in a metaphorical way that what we call space time is kind of the tip of the iceberg. So the idea is that, yes, the fundamental reality is what I call a quantum substratum. That's kind of a precursor domain to space-time, and that what we call space-time is really kind of a construct that is the results of measurement interactions. So those actualized measurement events that would be the emission event, the actualized emission event, the actualized absorption event, so the absorber that kind of won that photon, and then the photon becomes like an element of space-time. It connects. It actually connects the emission and absorption event, and it's an interval. So it defines an invariant interval. So whenever we got this measurement interaction and this actualized transaction, we get a new element of space-time. It's kind of a link. So it's not just an isolated event. They always come in pairs. There was an emission event, absorption event, and that structure. So that structure is just gravity. Okay, so the idea is that the metrical properties of space-time that are described by general relativity are emergent from this transactional process. So this kind of gives us a way forward for a quantum theory of gravity, which I don't claim to have, but I'm working with a colleague right now, Andreas Schlatter, who has already done some work on a version of quantum gravity. It takes off from what's called entropic gravity that was pioneered by Eric Verlinde. And he did very interesting work. He's still working on it. With the idea that again that space-time with its metrical properties that is that's all gravity is the metrical structure of space-time. So then he showed that this is really kind of an emergent property that has this entropic character, that the attraction of gravity is basically that, just simply that certain things are more likely to happen when you have areas of higher entropy, so that what looks like a mass moving toward another mass is simply a series of events that reactualize these two masses in a way that they're constantly getting closer, because that's like the entropically favorable state. So it's a really interesting way forward that that Andreas and I are working on fleshing out in this transactional picture.
Yeah, I really like Verlin's idea of, basically just the volume of space gives you more states. So you have this entropy, which is associated with masses that are far apart, and very elegant theory.
It is. It's wonderful. It's a very elegant theory, and so we're working with that, and we kind of think that the idea of transactions helps to explain kind of the information content. There's sometimes a little bit of hand waving about, well, why is the entropy, have this character? Why is your larger entropy, around in closer proximity to when the masses are closer together? So there's some work to be done to kind of quantify that, but the idea that the space-time construct is, again, it's not in our picture, it's not a container. I mean, that's kind of what we're up against in a kind of what we need is a paradigm shift here, because we all kind of grew up thinking that the word space-time means container for everything that's real, container for everything physically real. And so in the picture I'm working with, that's really not the case. And in fact, a lot of what's real is not in any sort of space-time container. It's a kind of a, if you will, it's a domain of possibility that gives rise to just this kind of tip of the iceberg manifold that is space-time. And that's really just a structured set of events that can be corroborated, so that we can send signals, and we can all corroborate that, yes, this event occurred, and we can give a well-coordinated, consistent description of an event through the use of communications, involving light signals. So that's kind of what the space-time structure is, but it's not a container for everything real.
Wow, I'm just rearranging my mind now.
Yeah, it does kind of turn your mind inside out. And I do talk about these more recent developments in my second edition that just came out, the Cambridge University Press. That the first edition came out in 2012, and it was called The Transactional Interpretation of Quantum Mechanics. Subtitle was The Reality of Possibility. So this one has the same main title, but the subtitle is now A Relativistic Treatment, because I've developed it a lot more in terms of the specifics of the relativistic features of the interpretation, because it really does go beyond the Kramer version on it, in a very, very specific ways. And I do have a chapter now on this idea of measurement via transactions as the mechanism for the emergence of specific space-time, units of space-time, and how does that work, and so on. So the book has different kind of levels, and the first half or so is more conceptual and hopefully fairly accessible in talking about the general concepts. But then the later chapters get a bit more technical and so on. But I believe chapter 8 is the one that has the information about this idea of space-time as emerging.
Yeah, I love the thought of this, because it it fits well with relativity and time dilation. If you think about photons and relativity and time dilation, anything that travels at the speed of light moves from one point to the other without any local time passing. So these transactions happen instantaneously from the point of view of the photon. The photon doesn't traverse space in its own frame. It is just at one particle and at the next particle. This is the framework that holds the universe together. That's I love that. It's good.
Yeah. And it's only from different inertial frames that it seems as though some time has elapsed between emission and absorption. But again, as far as the photon's concerned, no, okay, well, these events are connected really from the point of view of the photon. So it's only from, the point of view of systems that have non-vanishing rest mass that there's an experience of a time lapse. And again, that's not an invariant, thing at all. It depends on your relative motion, what kind of, time lapse you're going to record.
Well, I think we're getting towards the end of our time slot, and this has been really interesting, and I really appreciate you taking the time to explain all this to me and our listeners in a way that we can understand it. It's been great. I have one last question that I ask a lot of my contributors, and I'm interested to hear what kind of science fiction do you like to read?
Oh, science fiction. Well, it's been so long since I've read science fiction. But I'm an Arthur C. Clarke fan. I mean, I do like science fiction. I'm not much on kind of the classic literature. My sister's a poet, and she's the English major, and she's, I guess Arthur C. Clarke, The City and the Stars, was one of my favorite novels. And back when I was, a little kid, I guess I was around 10 or 12, back then they called it junior high school, library had this wonderful story called The Star Seekers by Milton Lesser. And it was just a wonderful story about basically, I don't want to give it away in case any of your viewers want to, but definitely look it up, The Star Seekers. And it was about basically kind of a journey, a multi-generational journey of people going from I guess the Earth to some extraterrestrial home. And great story, wonderful story. So, and I'm a Trekker. I like Star Trek, and I like Babylon 5.
Yes, it's got very good reviews. Indeed. So thanks again for coming on. I'm going to send you a Rational View t-shirt for taking the time to chat with us. So it's been a pleasure chatting with you. I hope we can talk some more about some of the philosophical implications of this theory, and look forward to learning more about it as we progress. Thank you.
I'd love to. Thank you again for the invitation. It's been fun.
If you'd like to follow up with more in-depth discussions, please come find us on Facebook at The Rational View and join our discussion group. If you like what you're hearing, please consider visiting my Patreon page at patron.podbean.com/TheRationalView. Thanks for listening.